Okay, I think we should start. It's my great pleasure to welcome Peter van Aken, who is the head of the Stuttgart Center for Electron Microscopy at the Max Planck Institute for metal research. And Peter has a very wide background, not only in microscopy, but across a whole board of different materials. And he has been, so he is still associated to the Technical University of Darmstadt, where he did his habilitation 20 years ago. And he is currently working a lot on the advancement of microscopy in general. And I think for the audience here, it is very important to notice that Peter is leading a program which allows people to use the best microscopes throughout Europe. And I hope England still counts to that. And this program is called STEAM, standing for Enabling Science Through European Electron Microscopy. And it allows researchers across borders to use the very best microscopes available at this point in time. I think I don't need to mention that he is not only highly cited, so he has been declared the world's among the first % of the people mostly cited, so highly cited in research. And I think that already speaks for itself. And today he will give a presentation about how sharp are atomically sharp interfaces in complex functional oxide heterostructures. So I'm very much looking forward to these amazing electron microscopy micrographs. Please take the scene, and I stop my video.
Okay, Katharina, thank you very much first of all for the invitation. Although I would have preferred to come over and to give the presentation at Imperial in London and not in my office here, where it's a little bit grayish due to the weather conditions here. Yeah, the title of my talk, How Sharp Are Atomically Sharp Interfaces in Complex Functional Oxide Heterostructures, was chosen due to a publication to which I will come soon. Well, I will surprise you with that. The outline of my talk is as follows. I will start with an introduction and tell a few words about methods, because I'm not sure whether everyone is really familiar with electron microscopy and the possibilities you have with that. I will come then to sample-related interface broadening, and then to detection-related delocalization effects when you acquire your signals. And at the end, a short summary. Interfacial studies of multifunctional complex oxides has been done already since ages. And when you have oxide interfaces, you will observe really exciting phenomena. And there was a nice publication by Harold Wang and co-workers where emergent phenomena at oxide interfaces were described. And it was a paper in Nature Materials here in 2012. When you have oxide interfaces, you may get a reconstruction of charge, spin, and orbital states, especially at the interfaces if you have two materials in contact. And this may lead then to superconductivity or to ferroelectricity or to magnetism and all these related effects. And there was the Nobel lecture of Herbert Krömer on 8th of December in 2000, and he said, often it may be said that the interface is the device. And I want to look at such devices and look at interfaces in more detail. And I want to link the chemistry and atomic structure of interfaces in these complex functional oxide heterostructures with the underlying physical properties. We grow our films via atomic layer by layer oxide molecular beam epitaxy. And you see here a picture of this machine, and here a sketch. And this unit is led by Gennady Lokvinov and two former PhD students, Erin Suyolcu and Federico Baiuti, grown these samples Here you have now the chamber, or a sketch of the chamber, where you have here different diffusion cells where you evaporate the metals and you deposit it here on your substrate. They can be immediately oxidized via an ozone source. And during growth, we have the possibility to observe the growth process via in situ read, where we have here the electron gun and here an electron detection camera. Furthermore, we've grown samples via pulsed laser deposition. And here you see a picture of the PLD system, where we have this PLD system in a UHV environment. We have here an excimer laser hitting on the target, and the material is sublimated and then evaporated and is grown here on our substrate. Again, we have here the possibility of in situ read control during the growth. If you compare now NBE and PLD, and you plot the techniques as a function of deposition energy, you see that for NBE, we have here a deposition energy on the order of 0.1 eV of the single atoms. If you now compare that with PLD, in PLD, we have here a deposition energy on the order of 10 eV. So that's at least 2 orders of magnitude higher than for NBE. And this has, of course, an also consequence for the final sample and the growth of the sample. So if you compare now PLD versus NBE, in PLD you have stoichiometric deposition of your material, whereas in NBE you have sequential deposition of your element, and you do that then layer by layer or atomic layer by layer, and the control of it is only in theory. In practice, it may be different, whereas in PLD, you have unit cell control. The deposition energy is on the order of 10 eV, whereas it is 0.1 eV for NBE. And the substrate temperatures are 750 degrees C for PLD, whereas it is slightly lower for NBE, where we have only 550 degrees C. The samples, especially if you work on oxide samples, they need to be annealed in an oxygen atmosphere at 0.5 millibar, whereas in NBE we have here 2.5 times 10 to the power of -5 millibars of ozone atmosphere, which is enough to oxidize completely your material. This means you don't need post-annealing for NBE growth, whereas for PLD growth you need to use or to apply a post-annealing in 1 bar oxygen atmosphere. If we have grown the samples, afterwards, we want to investigate them with electron microscopy. And we see here now 2 state-of-the-art TEMs, which are here available. These are 2 instruments by JOL. One is a probe-corrected with a D-core corrector, ARM 200F, and the other one is an image-corrected machine with a Z-core corrector from JOL. Both machines can be operated at 30, 60, 80, and 200 kilovolts. We have on both machines 2 large field Centurio STD type EDX detectors. Both are equipped with a GATAM GIF quantum ERS energy filter. Cameras are the quantum detector Merlin camera, the K2 camera on the GIF quantum, the GATAM Ultrascan XP1000 as the pre-filter cameras, and the Orias SC200D in case here for diffraction work. Furthermore, we have several TEM holders, single and double tilts, in situ heating and cooling, tomography, and in situ heating and biasing holders. With this, we can now acquire, and I will talk today mainly about HADF and ABF imaging, whereas HADF stands for high angle annular dark field imaging. And this means when we have here a highly convergent electron beam arriving on our sample, this beam is rastered across the sample, and we can now acquire pixel per pixel the high angle annular dark field signal. And this signal itself is proportional to the atomic number Z to the power of 1.8. This means it shows a high dependence on the atomic number, and it's ideal for heavy element imaging. And here you can see a HADF image of lanthanum strontium aluminate, where you can identify the lanthanum, the strontium, and the aluminum atoms. On the other side, you can also use the transmitted beam, and if you partly block this transmitted beam with the beam stopper, you can then obtain an annular bright field image, and this annular bright field image, or its signal, is proportional to the atomic number Z to the power of 1/3. And this means it's ideal for light element imaging. And you see now here an ABF image, which was acquired simultaneously with the HADF image. And you can now nicely see also here the atomic columns in this image. Besides ABF and HADF imaging, we also use some hyperspectral imaging, rastering the sample, the beam across the sample and acquiring either the EEL spectra pixel per pixel or the EDX spectra. And by doing so, you can then obtain a filtered three-dimensional data cube, or in the case, if you do it both at the same time, EDS and EELs, you acquire a four-dimensional data cube. And this brings me now to the first reason why we started looking at these interfacial properties and looking at the sharpness of interfaces. We had a very nice paper in Nature Materials in 2016. And we were there looking at long-range charge density wave proximity effects at cuprate manganate interfaces. The sample was as follows. We had a strontium titanate sample, and we grown alternating layers from blue yttrium-bearing copper oxide, 50 nanometer thick, and 10 nanometer thick lanthanum calcium manganate. And if you now grow the stack, we were then able to determine a kind of tomographic reconstruction. So we were plotting as a function of thickness, or as a function of position here, and critical temperature. Following, we had here our LCMO layer, here the UPCO layer, and here the LCMO layer. And we found that LCMO was a ferromagnet, whereas here the UPCO, or the interface region, became antiferromagnetic insulator. Then we saw a spin density wave region. The same on this side, ferromagnet, antiferromagnetic insulator, and here the spin density region. And then in between, we saw some superconductivity at low temperatures and a charge density wave at higher temperatures. The referees were then asking, well, can you prove that this material is really a single crystal and that you have really this structure? And we said, yes, of course we can. And we started doing, and that was the time when we came into this game for this paper. And we could show them here via STEM HADF imaging that we have here the LCMO, and here on top the UPCO, and here at the bottom the UPCO. And we were looking at the bottom and at the top interface. And if you look here at the interface, it looks really perfect. And we had an atomic level resolved structure, perfect epitaxial structure, and it was free from any undesired crystal defects. And then we measured by chemical mapping using STEM EELs, the structure again, and we obtained this image, and everything looked really perfect. We could identify yttrium-bearing copper oxide on the left and on the right side, and here the lanthanum calcium manganate in between. However, I was telling into my co-staff saying, hey, people, come on, let's look a little bit more detailed to this interfacial region. Because why is there here this contrast? And this contrast is really strange. And they were then looking at this contrast, and we're looking at the signals of the calcium L23, the yttrium L23, the lanthanum M45, the barium M45, and the manganese and copper L23 white line intensities. And you can nicely see here the yttrium signal in cyan, and here in red the calcium signal. However, if you follow the calcium signal, you see that the calcium is also present here in UPCO on the left-hand side as well as on the right-hand side. For the lanthanum and barium, you saw the same. You see that the barium signal here is still available here at the lanthanum calcium manganate, whereas there's also some lanthanum available here on the barium sides here in the yttrium-bearing copper oxide. And this is mainly on the lower how you call it, interface. At the bottom interface, it was here a lot sharper. And the similar behavior we observed here for manganese and copper. So the signals never went really to zero, and we still have intermixing here of these materials at these interfaces. So interface-wise, or the interfaces appear structure-wise atomically sharp, but chemically have a width of up to several nanometers. And now the question was, of course, when you look back at this tomographic reconstruction of this diagram, which I've shown you before, is this now, or are these now interfacial effects, or are these now effects due to some chemical redistribution of these elements which I've shown you here? And this question we could not answer during those days. And in principle, we cannot do it now neither. But I will explain you how one can disentangle and look at different interface effects. And I will start now with sample-related interface broadening. And sample-related interface broadening, let's start simple. We have now two materials, A and B. And just from a geometrical consideration, we have here material A shows here a step. Material B has been grown on top of material A. If you measure now your interface, or you measure now your EDS profile or your stem yields profile along this line, you get a concentration profile which looks like this. However, if you measure it now along this blue line here, then you get a different concentration profile, which looks like this. So you get here a step. And due to other effects, which I will explain later, you will get then some broadening here. This means that you have, due to this simple step, already some broadening effects, and you don't measure a clear profile. And that this trivial interface broadening happens, I will show you in the next slides, because we started studying lanthanum nickelate, lanthanum aluminate multilayers grown on lanthanum-strontium aluminate substrate. And here we have a surface step on our substrate. And if you now look at these multilayers on the left-hand side and on the right-hand side of this surface step, we see then that at this position here, where exactly the surface step was, we have here a stacking of A, B, A, B, A, and here it goes all again, A, B, and so on. So there is due to this surface step, there is a vertical shift of half a unit cell, and one B plane is missing. And we could show that also in stem yields investigations, and you saw that the nickel signal here is shifted just by half a unit cell, or also the lanthanum signal. And the origin of this two-dimensional Rutherford fold is just this surface step. We saw also in this lanthanum nickelate, lanthanum aluminate, three-dimensional Rutherford folds. You see here these fancy blocks here. And if you now look in more detail to these fancy blocks, you see here the clear contrast between these multilayers. But in this Rutherford fold area, you don't see it. And if you look now at the unit cell here on the left-hand side, in this Rutherford fold, the unit cell is shifted by half, and half, which leads then to overlapping of nickel and lanthanum or lanthanum and aluminum columns, and you cannot distinguish it anymore. That's the reason why this contrast looks like this and not like this anymore. And the formation of these Rutherford folds, especially the three-dimensional Rutherford folds, happens because initially you want to grow just lanthanum, nickel, lanthanum, aluminum, lanthanum, and so on and so forth. And this will give you this structure as a perfect growth. I've skipped all the oxygen atoms in order to make it more simple, but this would be just the cation structure. However, if you have now a stacking fold here, then you will not get the next layer of aluminum on top of it, but you will have aluminum here and then aluminum here on top of this one. So you will still keep this step. And this means if you now grow then the next layer of lanthanum, you will have then here still some aluminum, and so on and so forth. And this leads here to this vertical shift, and due to the overlay which we observed. And the origin is just the stacking fold or a service step in this case. I was talking about MBE versus PLD in the beginning. Here we have now a sample which has been grown by MBE and here the similar sample which has been grown by PLD. It's again lanthanum nickelate, lanthanum aluminate, multi-layers, grown on an LSAT substrate. LSAT stands for lanthanum strontium aluminum tantalate substrate. And you see that for the MBE grown sample, we have here a very sharp interface between the substrate and the lanthanum nickelate layer. And also between lanthanum nickelate, lanthanum aluminate, we have here really sharp interfaces, which you can see here from the contrast profile, which has been integrated in horizontal way, leading to this profile which you see here. For the PLD grow sample, you see that you have here several positions which are really bright, just underneath or below the LNO substrate interface. And this is due, or probably due to the implantation of lanthanum atoms into this lanthanum strontium aluminate tantalate substrate, leading to this brighter contrast. And also, if you now look at the interfaces here into the contrast, you see that the interfaces here are a lot more rough compared to the interfaces here for the MBE growth. And the rougher interfaces in the PLD grown samples are attributed to higher deposition energies in PLD, leading to the intermixing of elements. We had here several publications on that. It started here in 2012 on the Ruddles and Popperfolds in LNO, LAO, followed by, it was in Journal of Applied Physics, followed by a publication, Advanced Materials, where we were looking at layer selective control of lattice structure in oxide superlattices. And in 2017, we had then a comparative study of LNO, LAO heterostructures grown by PLD and by oxide MB. Okay, let's come now to the cuprate superconductors phase diagram. This generic phase diagram you probably have seen already 100,000 times, where you plot the critical temperature versus hole concentration. For low hole concentrations, you have here an antiferromagnetic insulator, followed by a region where you observe superconductivity at low temperatures. And if you increase the hole concentration further, then you will end up here with a metal. Lanthanum cuprate is a typical antiferromagnetic insulator. Here you can see the structure of it. And we want to grow the following. Excuse me. We want to grow a strontium delta doped system of lanthanum cuprate. And what does delta doping or strontium delta doping means? Well, we grow N half unit cells of the antiferromagnetic insulator lanthanum cuprate, followed by one layer of, or 1/2 unit cell of lanthanum strontium cuprate, which is a metal because lanthanum to strontium ratio is 0.5 or 1:1. And we repeat this R times. So our sample looks like one layer or 1/2 unit cell of strontium lanthanum cuprate plus N half unit cells of lanthanum cuprate times R. And just one delta doped layer is here illustrated by this wall of bricks. The red bricks are the lanthanum cuprate half unit cells, whereas the blue layer in the middle is just 1/2 unit cell of strontium lanthanum cuprate, followed by lanthanum cuprate. And we were aiming for unexpected interflational and functional properties. We know the blue layer is a metal, the red layers here are antiferromagnetic insulators. And if you now grow this material and measure it as a function of, or you measure the resistivity as a function of temperature, you all of a sudden observe unexpected interfacial superconductivity at higher temperatures. So we have here a high TC superconducting system, and depending on the number N of layers, we observe here superconductivity. So for N equals 0 and 1, we don't observe superconductivity. However, from N equals 2 up to N equals, was it here 19 or 20, we observe here a transition to superconductivity. with a maximum critical temperature on the order of 36 Kelvin for n equals 6, 5 to 6. Okay, we're then looking at this material. So again, we have here our lanthanum strontium aluminate substrate, lanthanum cuprate, here the first layer of lanthanum strontium cuprate, lanthanum cuprate, and so on and so forth. And we have here n equals 7, so 7 half-unit cells of lanthanum cuprate, 1 half-unit cell of lanthanum strontium cuprate, and we repeat this 8 times. You can see this here very nicely in this graph. And this is the growth direction, of course. So what do we observe? We have an atomic level resolved structure. Again, a perfect epitaxial structure free from any undesired defects. However, if you now look at the integrated, the vertically integrated intensity HADF profile, we just integrate here the intensity. You see here this profile, and I'll make it now a little bit more clear and put just a red line on top. You see here, it slowly increases, steeply decreases, slowly increases, steeply decreases, and so on. So this means we have here a kind of asymmetric profile, because we would have expected a profile which would be like a step profile, because it should be lanthanum cuprate, step down, lanthanum strontium cuprate, step up, lanthanum cuprate. But we see here a different profile. We did then measure via EDX the lanthanum and strontium concentrations. Since the lanthanum strontium aluminate substrate has a lanthanum to strontium ratio of 1 to 1, we know exactly that this should be 50% each. And we can then measure the lanthanum and here the strontium profiles, and can then determine the lanthanum strontium concentration. And we see that at the maximum here, we have a composition of lanthanum 1.66, strontium 0.34, copper 04. But that's of course far away from lanthanum 1, strontium 1, copper 04, for what we were aiming. And we see here very nicely this asymmetric strontium profile, not only in STEM EDX, but also in STEM EELs. This is the growth direction. And from the strontium L23 white lines in EELs, you see again here that we have here this asymmetric line profile. The asymmetric strontium concentration profiles from STEM HADF, STEM EDS, and STEM EELs shows the following. For the upper interface, we have a width on the order of 2.3 nanometer in growth direction. The bottom interface here from maximum towards 0 is on the order of 0.9. And we observe that for all interfaces. We did not look only at the strontium delta doped case, but also at the calcium and barium two-dimensional doped lanthanum cuprate. Here you see again the STEM HADF images, lanthanum calcium, lanthanum strontium, and lanthanum barium. You see for the calcium case, it's very clear, pretty sharp, strontium as shown as before. And for the barium case, we see that we have here a lot wider distribution compared to strontium or to calcium. Nevertheless, all 3 samples turned superconducting. So we observed this unexpected interfacial high-T superconductivity. And the question was now, why is that? And we need now to look first to these concentration profiles. So we were aiming for the nominal interface, which is shown here. We want to have a sharp, flat interface. However, from our concentration profiles of dopants, we see that we have the interface here. However, we have a lot of atoms, the dopants, above the interface, and also a few of the dopants below the interface. And we studied now the impact of the dopant chemistry in terms of dopant ionic size and charge by varying the dopant, calcium, strontium, barium, and by varying the growth conditions. So we're looking also at different growth temperatures. We always observed an asymmetric dopant redistribution across the interface, as shown here. And in growth direction, the dopant distribution is mainly determined by the growth kinetics. In downward direction, it is mainly determined by the thermal diffusion. So if you reduce the temperature, you see that this profile becomes narrower in downward direction. Nevertheless, we could describe this dopant profile by the segregation of the dopant at the surface during the growth, and that can be described via a phenomenological Muraki model. This model is known from the growth of semiconductors, where you have just at the interface a kind of liquid of the dopant, and if you grow down the next interface, this dopant is then pushed towards the next plane, and so on and so forth. And this is described by this Muraki model. And we could describe our dopant profiles using this Muraki model. Now coming back again to the superconductivity and the question why this material becomes superconducting. If you look at this multi-layer again, we have here lanthanum strontium cuprate, here lanthanum cuprate. And if you measure now the oxygen K edge in lanthanum cuprate, you see here this oxygen K edge. And the oxygen K edge is due to the excitation of oxygen 1s electrons into empty states, first of all with p symmetry, and then later on also to higher level states. And this gives rise here to this oxygen K edge profile. However, if you measure now your oxygen K edge in the delta dot layer here, you see that the profile itself looks in principle very similar, except that at the pre-edge, you observe here a feature, and this pre-edge feature can now be extracted because you can plot this red curve on top of the black curve, which is done here on the right-hand side, and you can extract here this intensity, and you can integrate this intensity. And then you have the integrated oxygen K pre-edge peak intensity. If you do that now as a function of light profile, position across your sample and across the layers, and you plot now the oxygen K pre-edge peak intensity as a function of distance from the delta dot layer, you observe here a symmetric hole profile. These holes are due to the excitation of a 1s electron, which goes into empty states with 2p symmetry due to the hybridization of the oxygen 2p orbitals with the 3d orbitals, which came available due to the hole formation. And this hole formation is always observed when your samples turn superconducting. However, we have measured also this asymmetric strontium concentration profile, which is shown here. And now we have two different profiles, the symmetric hole profile and the asymmetric strontium concentration profile. And this is now shown here. And with these two different profiles, we can now determine the mechanism when the material becomes superconducting. Because we saw above the interface that we have here a decaying strontium dopant profile, and that is just like a strontium concentration here, and it goes together with the hole profile, and that is just like homogeneous strontium doping, which creates electron holes. It's just like pure doping of lanthanum cuprate with strontium, and you form holes leading to superconductivity. So this material here on this side turns superconducting. However, here we have now the interface, and we see that the strontium dopant profile drops steeply and goes close to zero, whereas the oxygen hole profile is still here above zero. And we have here the symmetric hole profile. And this leads to the conclusion that we have here space charge effects. Space charge effects means we get here a separation of charges leading to the formation of holes here. And these space charge effects lead to electron holes, leading to the conclusion that this here turns superconducting as well. So we have in this sample two different mechanisms how this material turns superconducting. Above the interface, we have just homogeneous strontium doping leading to superconductivity, whereas below the interface, We have here space charge effects leading to the hole formation, leading to superconductivity as well. However, this might be at a different temperature or might be slightly different from the holes here. And that was the finding which we then started publishing in 2015 in Nature Communications. We had then 2 further publications in Applied Materials Interfaces on this topic in 2016, here and here. Then in 2017, we had another publication in Scientific Reports, and finally one in JOL News in 2018. Okay, coming now to the next topic, to detection-related delocalization effects. And we were studying now strontium manganate, strontium titanate superlattices. We started with a strontium titanate substrate and grow then 1, 2, 3, 4, 5, and 10 unit cells of strontium manganate, which were separated always by 7 unit cells of strontium titanate. Again, the sample looks really perfect, no defects in HADF as well as ABF imaging, and you can identify here the different layers. However, if you now integrate the HADF intensity profile, you can hardly recognize different SMO and STO layers. Although the structure itself is epitaxial, it's a perfect epitaxial defect-free structure. We were then looking at spectrum images acquired here from this green box. You see now here the titanium L23 and the manganese L23 spectrum images. And you see nicely the titanium signal, the manganese signal. You can color code it. You can create then an RGB image and this composite image, and you can identify different layers. Again, everything looks perfect. However, if you now look not to the color-coded images, but to the real concentration profiles, you see here for the 1, 2, 3, 4, 5, and 10 layers that at the interfaces here, there was always a substantial and a considerable chemical mixing between manganese and titanium. And this happens at all SMO-STO interfaces. So although the structure is crystallography-wise sharp, chemically we have here again considerable chemical mixing. We then grow just an SMO film on STO without any further interfaces, and we're then looking at the manganese and titanium signals at the interface. You see here that the titanium signal drops here at the interface, but we have here a titanium signal still in the SMO part, and this goes up to about 1.5 nanometer. If you grow SMO on STO, the growth was done by PLD in this case, you see that you also have manganese here in the STO substrate. And this is on the order of 0.5 nanometer, this width. So we have here an asymmetric elemental distribution, and we have about 0.5 nanometer signal spreading here in STO and 1.5 nanometer signal spreading in SMO. This brings me now to the detection-related effects for signal delocalization. Of course, we have on one side this chemical redistribution due to the growth. We have thermal diffusion and the growth kinetics, but we also have detection-related effects for signal delocalization. We have to think about our experiment. We're coming here with a highly convergent incoming electron beam rastering across the sample, and this electron beam stays convergent and goes through the sample. So due to the finite beam diameter and the convergence of the electron beam, you may detect not only the atomic column where the electron beam is positioned on, but you may detect other columns as well. And this may be due to multiple electron scattering within the sample. You may have electron channeling, but especially also electron dechanneling. And the dechanneling is as follows. When you have a high Z element column, for example, this column, then you get a refocusing. If you have here your incoming electron beam, you get a refocusing of your incoming electron beam on this column. So this means for HADF images, this signal is a highly localized signal. However, if your elements become lower, and you go into an intermediate Z or a very low Z element, your electron beam may channel off this column and channel to the next column and jump to the next column, and you get a channeling along this column, or even to the next column here to the side of it. And the problem now is that your detector doesn't know, which is here underneath, your detector doesn't know where this electron is coming from. It just measures it, this electron, and it measures then, for example, the energy loss or the electrons or the EDS counts on your detector, and therefore your spatial resolution is well, becomes worse. And the lighter your element is, the worse the spatial resolution comes due to dechanneling. And another effect is, which I didn't talk about at all, was thermal diffuse scattering. So when the electron beam comes here on your sample, you may excite phonons. And this phonon excitation gives you a broadening of your beam, which then again makes it easier to dechannel off the column and dechannel and channel along different columns. And then a final contribution is the inelastic Coulomb delocalization. And what does that mean? The inelastic Coulomb delocalization tells you something about the interaction if your electrons passing by your sample and even are not going through the sample. So if you are doing an aloof experiment, you have here your sample, the electron beam is just going next to it, and there is still then some interaction of this electron with your sample. And this inelastic Coulomb delocalization depends strongly on the energy loss edges you are looking at. There's a strong dependence of the inelastic delocalization on the energy loss, and this has been described by Ray Aken, especially in his Bible, Electron Energy Loss Spectroscopy in the Electron Microscope. And you see in that book this graph here where the delocalization is described as a function of energy loss. And the delocalization can be very large for very low energy loss processes on the order of up to several nanometers. Okay, what did we do then? We constructed a perfect crystal consisting of strontium manganate, strontium titanate, and we then calculated using an inelastic multi-slice simulation and especially using the mu stem code of Allen, and determined then the spectrum images and calculated the spectrum images for samples with different thicknesses. Here you have a sample thickness of 10 nanometer, manganese L23, the titanium L23, here the composite image, and here the concentration profile or the contrast of the different signals, type manganese and titanium. And you see that for 10 nanometer, you hardly have here intermixing. However, if you increase now your sample thickness to 50 nanometer, you see that you get a diffuse halo around your atomic positions. This is not only for manganese but also for titanium. And if you have now here your composite image and you plot here the concentration profiles, you see here that you have a redistribution of your, or extension of your manganese signal, and here your titanium signal, which is on the order of half nanometer into the neighboring material. So with increased sample thickness, you will obtain an increased electron scattering within the sample, and this will enhance your signal delocalization. And here is now the signal delocalization plotted as a function of thickness, whereas the signal delocalization has been defined as the difference between 95% and 5% of the maximum signal. And you see that for a sample thickness of 10 nanometer, the spreading is on the order of 0.25 nanometers, and it goes up to 0.7 nanometers for a thickness of 50 nanometers. So you will obtain a increased signal delocalization with growing sample thickness. Your delocalization effects as a minimum in the thinnest region, and this, of course, shows the need of inelastic multi-slice simulations to support your interpretation of your experimental data. And this results has just recently been published in ACS Nano, where we were studying, probing the charge accumulation at strontium manganate, strontium titanate heterointerfaces via advanced electron microscopy and spectroscopy. And it was just published in, I think, December last year. With this, I would summarize my talk and come to the end. I've told you about the sharpness of complex oxide heteroin interfaces, and it starts with sample-related interface broadening. This can be trivial geometric effects like surface steps in substrates or defects in crystal in your substrates. You can have growth method related effects when you compare PLD versus MBE, and you have thermal diffusion and growth kinetics, which gives you different profiles. And then you might have detection related delocalization effects, where you have to name the finite beam diameter and the convergence of your incoming electron beam. You have multiple scattering depending on the thickness of the sample. You have electron channeling and especially electron dechanneling, where the electron beam jumps to the neighboring atomic columns. You have thermal diffuse scattering by excitation of phonons, and you have the inelastic Coulomb delocalization, and all these effects will broaden your interface. The knowledge of the interface sharpness plays a major role in understanding the underlying physics. However, after so much bad news I've told you during this lecture, the good news is that analytical electron microscopy reveals the upper limits of the interface width, which means we're always better than what we determine in our experiments. And that is really the good news of it. With this, I would like to acknowledge the intense collaboration with the following people. Without their contributions, work wouldn't have been possible. So it's from the scientific facility, thin film technology, it's Gennady Lokminov, Leo Christiani, Hans-Ulrich Habermeyer, Joachim Meyer, Federico Baiuti, Giuliano Gregori, Bernhard Keimer, Eva Benkieser, Alex Fragno, Matteo Minola, and Federico Wobel, Jochen Mannhardt, Hans Boschke, and all STEM staff members, where you see just the recent, well, recent is already 1 year old, group picture taken in Ringberg Castle. Here's Aaron and Yi Wang and Hong Wang, who did most of this work, which I've presented today. And with this, I would like to acknowledge financial support by the Max Planck Society, the German Science Foundation, the Bundesministerium für Bildung und Forschung, the Alexander von Humboldt Foundation, the European Commission for funding STEAM 1, STEAM 2, and STEAM 3, and the Chinese Academy of Science. And I want to use the last words for STEAM 3. STEAM 3 is an integrated infrastructure network of European electron microscopy facilities providing transnational access for the academic and industrial research community in materials, physical, chemical, and life science to the most powerful electron microscopy instrumentation and techniques available at the moment, and this at the nanoscale. You will obtain free transnational access to these partners: Trondheim, Göteborg, Krakow, Graz, Ljubljana, Catania, Stuttgart, Jülich, Antwerp, Orsay, Cambridge, Oxford, Toulouse, Saragossa, and Cadiz. And you can look it up at the STEAM 3 website. And free transnational access means you can either go there, bring your samples, do the experiments there, and how to do that is described here on the website. Besides this transnational access, we also develop joint research activities for advanced electron microscopy methods required for the solution of key problems in studying materials for ICT, energy, health, and transport. And we also support automation and big data treatment. Furthermore, we have also networking activities, and we implement a wide variety of activities aiming at improving the dissemination of outputs such as open access publication in high-ranked journals, lectures at selected conferences. We have set up an educational hub, which you can look up at the website, and we have organized a series of schools, workshops, and webinars where you get training by specialists in advanced techniques. And this you can find all on our website. there's also a news part where new workshops and schools are announced. With this, I would like to thank you for your attention. Thank you very much. And if you have questions, I'm open for any questions.